Hello and welcome back to another video. Today I am going to talk about basics regression in TensorFlow and also how to predict fuel efficiency. This video is in part of my TensorFlow series. Before we start, please check out my newsletter. The entire source code and explanation is published there. You can find the link to my newsletter in the description. So let's start. In a regression problem, the aim is to predict the output of a continuous value, like a price or a probability. Contrast this with a classification problem, where the aim is to select a class from a list of classes, for example, where a picture contains an apple or an orange, recognizing which fruit is in the picture. This tutorial uses the classic AutoMPG dataset and demonstrates how to build models to predict the fuel efficiency of the late 1970s and early 1980s automobiles. To do this, you will provide the models with a description of many automobiles from that time period. This description includes attributes like cylinders, displacement, horsepower, and weight. The dataset is available from the UCI Machine Learning repository. Retrieving the dataset. First, download and import the dataset using pandas. Now the next thing we are going to do is to clean the dataset. The dataset contains a few unknown values. Drop those rows to keep this initial tutorial simple. The origin column is categorical, not numeric. So the next step is to one-hot encode the values in a column with pd_get_dummies. Split the data into training and test sets. Now, split the dataset into a training set and a test set. You will use the test set in the final evaluation of your models. Inspect the data. Review the joint distribution of a few pairs of columns from the training set. The top row suggests that the fuel efficiency, MPG, is a function of all the other parameters. The other rows indicate they are functions of each other. Let's also check the overall statistics. Note how each feature covers a very different range. Split features from labels. Separate the target value, the label, from the features. This label is the value that you will train the model to predict. Split features from labels. Separate the target value, the label, from the features. This label is the value that you will train the model to predict. Normalization. In the table of statistics, it's easy to see how different the ranges of each feature are. It is good practice to normalize the normalization layer. The tf.keras.layers normalization is a clean and simple way to add feature normalization into your model. The first step is to create the layer. Then, fit the state of the preprocessing layer to the data by calling normalization.adapt. Calculate the mean and variance, and store them in the layer. When the layer is called, it returns the input data, with each feature independently normalized. Before building a deep neural network model, start with linear regression using one and several variables. Linear regression with one variable. Begin with a single variable linear regression to predict MPG from horsepower. Training a model with tf.keras typically starts by defining the model architecture. Use a tf.keras sequential model, which represents a sequence of steps. There are two steps in your single variable linear regression model. Normalize the horsepower input features using the tf.keras.layers normalization preprocessing layer. Apply a linear transformation to produce one output using a linear layer, tf.keras.layers dense. The number of inputs can either be set by the input_shape argument, or automatically when the model is run for the first time. First, create a number py array made of the horsepower features. Then, instantiate the tf.keras.layers normalization and fit its state to the horsepower data. Build the keras sequential model. This model will predict MPG from horsepower. Run the untrained model on the first 10 horsepower values. The output won't be good, but notice that it has the expected shape of 10, 1. Once the model is built, configure the training procedure using the keras model.compile method. The most important arguments to compile are the loss and the optimizer, since these define what will be optimized, mean_absolute_error, and how, using the tf.keras.optimizers, atom. Use keras model.fit to execute the training for 100 epochs. Visualize the model's training progress using the stats stored in the history object. Collect the results on the test set for later. Linear regression with multiple inputs. You can use an almost identical setup to make predictions based on multiple inputs. This model still does the same, y equals mx plus b, except that is a matrix and is a vector. Create a two-step keras sequential model again with the first layer being normalizer, tf.keras.layers, normalization, axis equals -1, you defined earlier and adapted to the whole dataset. When you call model.predict on a batch of inputs, it produces units equals 1 outputs for each example. When you call the model, its weight matrices will be built. Check that the kernel weights, the m in y equals mx plus b, have a shape of 9, 1. Regression with a deep neural network, DNN. In the previous section, you implemented two linear models for single and multiple inputs. Here, you will implement single input and multiple input DNN models. The code is basically the same except the model is expanded to include some hidden nonlinear layers. The name hidden here just means not directly connected to the inputs or outputs. These models will contain a few more layers than the linear model. The normalization layer, as before, with horsepower_normalizer for a single input model and normalizer for a multiple input model. Two hidden, nonlinear, dense layers with the ReLU activation function nonlinearity. A linear dense single output layer. Both models will use the same training procedure, so the compile method is included in the build_n_compile_model function below. Regression using a DNN and a single input. Create a DNN model with only horsepower as input and horsepower_normalizer, defined earlier, as the normalization layer. This model has quite a few more trainable parameters than the linear models.